Hello, everyone. I hope you're doing well today. Now we will talk about Chapter 7.2. We're going to be working with paired data to study the parameter for paired data. We're going to use simulations. So basically, we're going to use the same simulation procedures we've used in previous chapters. Let's do a quick review of what paired data is. Data is observed in pairs. Each observational unit is a pair of subjects. In paired data, we're going to know that a subject in group 1 is related to its partner in group 2. The classic example is identical twins. I've talked about pigs in the same family, or a person doing something twice in different scenarios, or people with the same BMI, people with the same demographics. You could have students in the same class or same major be a pair. These designs, the paired designs, are very beneficial when you expect a strong association between the observations in a pair. Plants of the same phenotype and could also be a pair. The response variable in paired design is a difference between two groups. This difference can be positive and negative. The parameter for this response quantitative variable is mu, that fancy u with a little d underneath it. This mu, or u, if you want to say it in words, is the long-run mean difference of blank, whatever is in your study, between group 1, whatever that is in your study, and group 2, whatever that is in your study. So it's a long-run mean of all the differences between group 1 and group 2. The null hypothesis is we assume that the long-run mean of all these differences is 0. In other words, we expect the two groups to give the same measures on average. Therefore, the long-run mean difference is 0. In the alternative hypothesis, we think that the long-run mean difference is not 0. When I say not 0, I mean greater than 0, less than 0, or not equal to 0. Read the question carefully to know if we are expecting a difference greater than 0, a difference less than 0, or a difference that's just a general difference, which means not equal to 0. We don't actually know what the parameter is, we're just making two hypotheses about that. So what we do, we gather a sample of data. This sample is a sample of observational unit pairs. We're going to find the difference for each pair and find two sample statistics. First sample statistic is the sample mean of the differences between the two groups. That sample mean difference is x bar over d, or x bar with a little d underneath it. Then we're going to find the sample standard deviation of all the differences. That symbol is s with a little d underneath it. There are two types of paired designs. First is repeated measures, where each subject is measured twice, once in one group and once in the other. Their two measurements together equal an observational unit pair. The second type is called match pairs. You're going to take two observational units you believe are strongly related with each other. They're very similar to each other, and you pair them up. One subject you'll put in one group, the other subject will be in the other group. Paired designs actually eliminate confounding variable effects except two confounding variables. The first confounding variable is the order of tasks. You don't want the task A to always be first and task B to be second. Instead, you want to randomize and say group A is first for this pair, group B is first for the second pair, group A is first, group A is first, group B is first, group B is first, and so on. That would be for our repeated measures design. You'll just randomize which task or group is measured first, like I did just barely. Group A is first, group B is first, group A is first, group A is first, group B is first, and so on. If you're doing a match pairs design, you just simply need to do random assignment within that pair. So just randomize which group goes to one of the subjects in the pair. The second confounding variable is called a carryover effect. You can have a rest period to eliminate that carryover effect. Some carryover effects are the following. Fatigue. Well, what can you do to get rid of fatigue or tiredness? You rest. So you just rest for a period of time, like a day or a week. Even a few hours could be fine. If you have drugs or food in the body, all you need to do is poop it out. Just get rid of it. So you could wait for a period of time to get rid of that drug, of that food. For the drug, you just have it leave the blood, and then your rest period is done. Okay, let's get into the new material here. If we want to do simulations, the basic idea is we want to generate more samples of the same sample size from the population. Well, we can't necessarily draw a bunch of different samples other than the sample we got. So we're going to use computers to do this. Remember, when we're performing samples, we are assuming the null hypothesis is true. Therefore, we assume that the explanatory variable is not associated with the response variable. In other words, we assume that the long-run mean difference is 0. If we assume the long-run mean difference is 0, there's no association. That means we think the two groups are the same. And so let's say we have group A and group B. According to the null hypothesis, we are thinking A is the same or similar to group B. If A is similar to group B, then there won't be a problem if we shift or swap some of the measurements around. So I'm saying that each star is a measurement for this example. We can just once in a while swap the two measurements within a pair and not suffer any consequences because A is similar to B. So there won't be a problem if we swap them. Swap the two measurements within a pair. The difference will be the same. reach out to me if you have further questions. The book has a good step-by-step example. But just remember, we think the two groups are going to be the same according to the null hypothesis that we made. So we can swap the two measurements within a pair, and the differences between the groups will still average out to 0. So if we want to do simulations, we only need to follow this process. We go to one pair at a time. We can just flip a coin. If it's tails, we're going to keep the measurements in the same groups. So the first measurement will still be the first measurement, second number will still be the second number. If we get a heads, we can just swap the measurements. The first will now become the second will now become the first. We would calculate the new difference after swapping or staying. And we'll do that for each pair. We'll average out the differences in our quote-unquote new sample of data. And then we'll repeat steps 1 through 4 many times. In class, we've done 1,000 times, 500 times, or any amount of times that you would like. Here's a little example. I'm wondering if a person's dominant hand can click at a different speed than their other or weak hand. Last semester, I asked each of my Stat 218 students to see how many clicks they could do in 5 seconds. I randomly assigned which hand the person used first. For some students, they use their dominant hand first. For the other students, they use their weak hand first. I didn't do a washout period for the students, so there was no rest between the first attempt and the second. And these data in this table right here are 5 of my students. Student number 1 had 32 clicks in 5 seconds with their dominant hand and 27 clicks with their weak hand. So if I found the difference for student 1, it'd be 32 minus 27. That equals a positive 5. We can find the average of the differences for these 5 students. Really, you just average up 5, 13, -1, 8, and 8 to get a sample mean difference of 6.6. So now I want you to do 2 simulations with these 5 students and calculate new sample differences. I would encourage you to pause this video to try it out yourself. If you want to see me do it, feel free to continue to watch. Okay, so for the first simulation, I'm going to go to student 1, and I'm going to flip a coin. Let's go. Flip. I got a tails. So I'm going to keep students 1's measurements as 32 first, 27 second. Okay, now student 2. I got tails again. So student 2 will have 45 first with their dominant hand and 32 second. For student 3, I got a heads. So I'm going to switch these two around. Now 34 will be first, 33 will be second. And since that's the case, I will go 34 minus 33 for my first simulation and have a difference of positive 1. Student 4, I got a tails, so I'm going to keep 34 first and 26 second. And student 5, I got a heads, so I'm going to switch these two measurements. I'm going to have 24 minus 32 equals a negative 8. So these are my new differences in my first simulation. I'll average out these differences, and that will result in a new sample statistic. That new sample statistic is 3.8. Okay, let's do our second simulation. I'm going to write this simulation with a orange color. Okay. I'm going to use orange arrows for the second simulation. Right here, I got a heads for the first student. So these two numbers, 27 and 32, are going to switch places. I'm going to find a new difference for student 1, which will be 27 minus 32. That equals a difference of negative 5. Okay, now for student number 2, I'm going to switch places again because I got a heads. Now 32 is going to be first, 45 will be second. So I'll have 32 minus 45. The new difference will be a negative 13. For student number 3, I got a tails, so I'll keep the order the same, and I'll have the same difference of negative 1. For student 4, I got a tails, so I'll keep this order the same here. 34 minus 26 equals the same difference of positive 8. And then for student number 5, I got a tails, so I'm going to keep the order the same and have a difference of 32 minus 24 equals positive 8. Now my new average difference of these 5 people will be negative 5 minus 13 minus 1 plus 8 plus 8 summing all those negative and positive numbers together equals negative 3. I'm going to divide that sum by 5, and that's going to be negative 0.6. So this new sample statistic, I'll mark that with x bar d star star. 2 stars means the second simulation. It's negative 0.6. My new sample statistic only after one simulation was 0.38. And then the sample statistic with our observed sample was 6.6. We'll do this process using the computer many more times. So we'll get a bunch of different sample statistics from our simulations, put them all in a plot. That plot will be a null distribution. So we'll do 1,000 simulations. Get a null distribution of all these different sample differences with stars. And that null distribution will help us find the p-value. And it can also help us find the standardized statistic and the confidence intervals. Then we can make a conclusion. So if you want to do simulations with a computer, I would highly recommend that. You can use the Match Pairs applet. I gave you steps to walk you through how to use that applet on your own. I'll show you how to do it myself, and so that you'll be more familiar with how it goes about. I'll do it using an example. On Canvas, there is a file that you'll open up in Excel, and you'll copy and paste that file into the applet. Before we do that, let's read some important information. First, this file, Chapter 7 speed test, came from the same question that you worked with when you talked about how many clicks can a person do in 5 seconds with their dominant hand, and then how many clicks can they get in 5 seconds with their weak hand. These are the 26 students in my class. So there are 26 observational units. Therefore, there are 26 pairs of student measurements. I took all those 26 students, averaged out their differences between their dominant hand and their weak hand. The sample statistic was an average of 2.808. I took the standard deviation of those 26 differences, and that standard deviation was 4.561. I gave you the null and alternative hypothesis, because I'm generous. I thought that the long run mean difference in the number of clicks a student can do with their dominant hand versus their weak hand was 0. Meaning I'm assuming that students can get, in the long run, the same average number of clicks in the dominant hand versus the weak. The alternative hypothesis is, I think the dominant hand can get more clicks than the weak hand. Therefore, I think the long run mean difference in the number of clicks in 5 seconds for the dominant hand versus the weak hand is greater than 0. Knowing these pieces of information, let's try to do this problem using the applet and see which hypothesis we want to go with and conclude. Okay. I'll find that file on my computer. Here's the data. You can see I have 26 students right here. A student did this test with the dominant hand and with their weak hand. I'll just copy the data by highlighting it and hitting Control C as in cat. I will go to Canvas, open up my applet, then on the top bar you'll see the Match Pairs tool. I'll click on it. The first step I need to do is I need to copy the whole thing and paste it all into this text box. After I pasted it in, you can click Use Data. And here's how the applet works. It shows the graph of all the measurements for the dominant hand. It shows the corresponding measurements for the weak hand. And it draws little lines to tell you this dot is paired with this dot that's in the weak graph. So it shows which 2 points pair up with each other. This bottom graph right here you see is labeled differences. It visualizes the differences for the 26 students in a little histogram. And you can see that if we average out all these 26 differences, you get a sample mean difference of 2.8. Then the standard deviation is also told to you. Standard deviation of the differences in our samples 4.561. Okay, so the data looks like it lines up well with the information that we know. So let's perform simulations using the randomize button. I'll show you how the applet performs one simulation to make sure you understand this concept even more. So I'm just going to leave 1 in the text box and I'll hit randomize. You'll see some coins right here. You'll see how they work one by one. So it flips a coin, keep first pair, it has the tails, so it keeps 32 first, 27 second. The fourth pair had a heads, so it switched 34 and 26 and had 26 first, 34 second. So they swapped places. Now they had a difference of -8, where beforehand they had a difference of +8. I did this for all 26 people in the study. Found a new difference, a new sample mean difference, and put that new sample mean difference of 0.115 into this plot, right by 0. You can see that there's a fair amount of points that swap places. Beforehand, we had all red dots in the dominant hands graph, but now we have a mix of red and blue dots in the dominant hands graph. Okay, let's perform 999 more simulations so that we have 1,000 simulations total. Unclick Animate button so we can do these simulations quick. So we did 1,000 simulations, plotted all the sample mean differences on this plot. This plot is a good guess on what our null distribution is. The center of this null distribution is almost 0. The center of this null distribution should be the parameter according to the null hypothesis. So we think the long run mean difference is 0, and therefore the center of this null distribution should be really, really close to 0. And it is. Perfect. The standard deviation right here is also really important. I'll show you what it is soon. Okay, so we want to find a p-value. See if there are any simulated mean differences that are as extreme or more extreme than our sample mean difference of 2.808. Can you locate 2.808 on this graph of the null distribution? Where is it? I see that 2.808 is about right here. I'll draw a line for you. I think 2.808 is about right here. Were there many simulated mean differences that were more extreme than 2.808? I don't think so. You see there's not really that many dots even past or outside of 2.808. We can even check yeah, so therefore I expect that the p-value is going to be very small. And we can use this count samples tool to find what the p-value actually is. So we're going to count all the simulations that had a sample mean difference that was at least as large as 2.808. Please note that you can change this drop-down menu to be greater than, less than, or beyond. How do you choose between the three? Look at your alternative hypothesis. What is the sign of that alternative hypothesis? In our case, the sign is greater than. So you're just going to simply put the greater than sign right in this menu. Okay, let's count all the simulations that are greater than or equal to 2.808. Wow, there was only one. One of the 1,000 simulations had a sample mean difference greater than or equal to 2.808. Divide 1 by 1,000 and we get our p-value of 0.001. Okay, so we calculated our sample statistic. We performed a simulation and even more simulations, made our null hypothesis, and we counted how many statistics were as extreme or more extreme than the sample statistic. So, if we were to make a conclusion, would we reject the null hypothesis, knowing what our p-value is? Or would we fail to reject our null hypothesis? Well, this p-value is definitely smaller than our significance level of 0.05. Let's say our significance level would be 0.05. Is a p-value smaller than our significance level? Yes. So we will reject the null hypothesis. If we reject the null hypothesis, what are we going to conclude? Yeah, if we reject the null hypothesis here, what will we conclude? We will conclude that the long-run mean so if we reject the null hypothesis, we're going to conclude the alternative hypothesis is true. And we'll say the long-run mean difference in the number of clicks students can do in 5 seconds between the dominant hand and the weak hand is greater than 0. In other words, students can click faster with their dominant hand than they can with their weak hand. That conclusion makes sense to me. Okay, when we performed our simulations and we got a null distribution, you can still use these simulations to find the standardized statistic and the confidence intervals. What do I mean here? So, remember that the general templates for a standardized statistic and a confidence interval are the following. First with standardized statistic. You take your statistic minus the parameter according to the null hypothesis over standard error. We need 3 pieces of information to find the standardized statistic t. Well, what's our sample statistic? Our sample statistic was x bar d. the parameter, according to the null hypothesis, is 0. You can just look at your null hypothesis for that value. And then the standard error is shown in your null distribution plot. That is the standard deviation of your 1,000 simulations and their sample mean differences. So that standard error is marked with the 2 stars that you see up there. After these 1,000 simulations that I ran when I made this image, my standard error was 1.005. Remember, the definition of standard error is your standard deviation of your sample statistics. This graph shows all of the sample statistics. Their standard deviation is the standard error. When we did our practice problem, let's go to the applet. We had 1,000 simulations to make our null distribution. The standard deviation of these sample statistics is 1.037. 1.037 is our standard error. You see my mouse hovering right here? That is our standard error. So we have the 3 pieces of information we need to find our standardized statistic. Yay! I'll save this for you. Okay, let's talk about how we find confidence intervals. The general template for confidence intervals is the following. You take your sample statistic. That's the center of your confidence intervals. And then you go in the positive direction and in the negative direction, plus or minus, multiplier times standard error. Well, what is our sample statistic? Oh, it's X bar with a little d underneath it. Yay. Our multiplier, you memorize. A common multiplier is 2. Another common multiplier is 1.96. That's for 95% confidence. And then the standard error. You can find the standard error in the same location of your graph. It's a standard deviation, all the sample statistics. And you can put the important pieces of information in. This is 1.96. I'll make that more clear. Okay, you put the statistic in at the beginning. You put your multiplier in as the second piece. Last piece of the puzzle is the standard error, and you get a lower bound and an upper bound. L for lower, U for upper. And there you have the confidence interval. So yeah, remember when you do simulations, the standard deviation of sample statistics is your standard error. I'll save this as well. Awesome. And we are done with 7.2. Reach out to me if you have any questions. I'm happy to help. And good luck.